We are talking about solving limits analytically, and we're looking at some of these theorems to show what our limit is actually equal to. We have this particular theorem here, the functions that agree at all but one point. Let C be a real number and f of x equal g of x for all x except at C. If the limit of g of x as x approaches C exists, then the limit of f of x also exists. And therefore we could say that the limit of f of x as x approaches C is equal to the limit of g of x as x approaches C. Let's take a look at an example. So this is our function here, which I'm calling f of x, and our function is x minus 1 over x squared minus 1. So in the previous theorem that I just read, this here would be my f of x. We do the direct substitution first, and so I plug 1 directly into the function. As you can see here, we have 1 minus 1 over 1 squared minus 1, and we end up with 0 over 0. So this is an indication that we need to do something with this to try to avoid this 0 over 0. And so what I do is I factor the bottom, and x squared minus 1 factors nicely into x minus 1 times x plus 1. Now what we can do is we can cancel. We have an x minus 1 in the numerator and an x minus 1 in the denominator, so we can actually cancel those out. And so now we're left with 1 over x plus 1. Now we have a new function, so which I'm calling g of x. So our g of x here is 1 over x plus 1. And then we do the direct substitution. We plug 1 directly in now, and as you can see, we get 1/2 out. So we started with a function which I called f of x, and we did some manipulation and we got a new function. Let's go back to the theorem. So our first function, which we say here in this theorem, is equal to the second function for all x except where x is not equal to C. And we say if the limit of g of x as x approaches C exists, then the limit of f of x also exists. So this was our first limit that we were looking at, except we got 0 over 0. And then we did some manipulation. We factored the denominator, canceled some terms out, and we ended up with a new function which I'm calling g of x. Now it agreed all but at one point, and that was C. As you can see, x approached C. Let's go back and take a look at that. And our C in this particular case happened to be 1. So in this particular function here, it was undefined at 1, because we ended up getting 0 over 0. And then we just canceled some terms out and got a new function. And our new function was x over x plus 1. However, both of these limits are equal to each other according to the theorem. Except, remember, for all x, except when x is not equal to C. And we ended up with 1/2. So as you can see here, I've got 1/2 written here. Let's take a look at the graph quickly. So I'm locating 1 here on the x-axis, and this is the graph of our function f of x. Except if you've noticed here, there's not a hole in the graph. It's not showing up. When you graph these functions, you won't actually see the hole in the graph. But there's an undefined point right here. If I find x or 1 on the x-axis, go directly up. However, it's not showing it, because our function f of x at x equals 1 undefined, which means that there's a hole right here in the graph.